Sure.
Give me a sec, okay?
Yeah.
So I should share my screen. Here we go.
Perfect.
Can you see my screen? Can you see the title, the thing?
Yes, we see your screen and we hear you well. We see you. Great.
Awesome.
So yeah, I think you can start.
Okay, thanks. So welcome everyone, and thanks Chirag for having me. One thing before we dive into AI interpretability, because you are stuck with me on the screen for the next hour. So to make up for this, I want this to feel like a conversation between I and you, not me talking at the word all the time, or at the word all the time. So here's the plan. We will have 4 parts, and after each part, I will stop for a few questions. If you have you just raise your questions. So today's topic is AI interpretability. The narrative is we are moving from tools that explain an AI after we build it to the AI that is transparent by design. So, okay, let's dive into the AI interpretability. So a quick housekeeping before we start. Interpretability is really a tongue twister for me. So sometimes I will just say interp for short, and mechanistic interpretability, I will shorten to make interp. So okay, let's just dive in. So let's rewind a little bit. We are going back to the dinosaur days of interpretability, and I promise it's kind of fun. So the first question, what is AI interpretability, right? AI interpretability means explaining how an AI model makes a decision so a person can understand it and trust it. But why do we even care about the model interpretability or model explanation? For the 3 reasons I argue, the first one is we want to trust AI models. We want to catch their mistakes. And finally, we want to make the model we are using to be safe. The question I want you to hold for the whole talk is, when an AI gives us an answer, can we tell why? Okay. So let's make this a little bit more concrete, because you're probably using AI every day. For example, when Spotify or YouTube Music recommends a song, or your phone auto-completes a word, do you care why it did that? Usually it's not. If it's wrong, you just skip the song or the completion. But now picture an AI that reads your essay and flags it for the plagiarism, or a system that decides a loan or a medical chatbot telling you what is wrong with your body, right? In those cases, just a model answer is not enough. And you want to know why it decided that? Here's the thing. The more we ask AI for decisions, the more we need to see its reasoning. So this fun interpretability is not new. It has been around far longer than today AI chatbots like ChatGPT or Cloud. It got popular with images. For example, you can highlight which parts of a photo made an AI say cat back then, like I think like more than almost 15 years ago. Then AI chatbots arrived, ChatGPT, Cloud, Gemini, and they brought many new problems. They sometimes make things up, and they say it with the total confidence. So if you look at this example, someone asks a medical question: can I take ibuprofen with my blood pressure pills? And if you look at the reasoning here, the model is basically thinking, this seems routine, so I will just give the yes answer, right? And its answer like, hey, take it, it's completely safe. That answer is wrong. And in medicine, a confident wrong answer can be dangerous or fatal. So the circle part here is the model explaining its own thinking, or people call it chain of thought these days, which is one simple kind of self-explanation, the model explaining itself. So there's another way to explain the AI after we build it, and we explain them by like external tools. Researchers call that post-hoc methods, and that's where we are heading next for the next part of the talk. Okay, so I just give you the background and the very history of the interpretability, why we need AI. So I will stop here for a bit for any questions. If no one has, I just move on.
Let's see. If anyone has any questions? Okay, I think we can continue.
Okay, sounds good. So we got the background of AI interpretability. And in this part, because we know that AI can self-explain itself, and there's another way to explain AI models. It is we are using external tools to explain the model we are trying to explain. And this is an ambitious one. So in the community right now, we have something called mechanistic interpretability. And so basically what we are doing is we open up a chain model and look at the parts inside. So let me dive into it. Okay, so a little bit of the background. There are actually many ways to explain an AI models. We already met one, the AI explaining itself, which can be unreliable, as I told you. The second big family is post-hoc interpretability, the middle one here, where we explain the AI after we build it. And the third one, which we will get into later, is by design interpretability, where we build the AI to be interpretable from the start. And there are many other, for now, we are just zooming into the post-hoc method for like a mechanistic interpretability here. Okay, so let's look at a popular and powerful tool for mechanistic interpretability, the sparse autoencoder, or SAE. Here's the problem it solves. A single neuron usually fires for many unrelated things at once. For example, just one neuron in our normal network will activate for the cats, for the color red, and for Python code patterns. We call that polysemanticity, meaning a neuron containing many semantics or many meanings. So an SAE here, it rewrites that dense activity or dense activation of the original model into a sparse set of features. And the goal is that one feature lines up with one human understandable concept so that every model prediction can be explained by a set of human concepts. Okay, so here's an autoencoder or SAE. On the left is an activation from the model you want to explain, X. It is dense, meaning every number is doing multiple jobs at once. The encoder, this encoder, it maps X into F, a much wider and sparse vector that is almost zero, where each active entry here, you can see the blue one, this stands for one concept. Then the decoder take the F here and try to rebuild or try to reconstruct the original activation. And we got the X head. And so a popular question is why we are reconstructing the activation. The reason is because if you can rebuild X here, the original one activation, from just a few active concepts, those concepts must capture what the original activation was really doing. We then read the sparse activation or the sparse feature F here as the explanation for the original dense activation or the black box model here. Okay, so here is how we chain an SAE. To chain the SAE on, we chain the SAE on lots of activations from the model we are trying to explain. The loss function have two parts. The first is a reconstruction activation. So the X hat here should match the original X, activation X. Second, the sparsity penalty, the lambda times the L1 norm of F, which forces most features to be zero. So only a few activate at once. We want sparsity here for human understanding and easy control over the output. Then at the test time, we fit a new activation from the original model, run just the encoder to get the sparse feature F and read which features turned on. This works pretty well on the real models like cloud. Here's a fun example from Anthropic. So they found a feature inside cloud that activates for the Golden Gate Bridge in San Francisco. Then what they did is they turned that feature up. Now, if we watch, someone asks a totally ordinary question, what should I do with $10? And the model now cannot stop talking about the bridge. It tells you to go pay the toll and enjoy the orange towers. So I think it's pretty funny, but the point here is kind of serious. Like finding a feature means we can also steer it and control the model output. That is, we tune it up or down to push or control the model behavior. The interesting model steering, we will come back in the next part of the talk. The Anthropic researchers, they also found the safety relevant features, like ones for unsafe code generation, the deception of users, and the bias. I think that is a strong use case for this whole approach, mechanistic interpretability. So I want to give it the real credit here before which I show that it's actually struggle. Okay, so all good. So far, mechanistic interpretability is working so well. It can find you like a super interesting features like a bias, a deception, or like a Golden Gate Bridge. But the first problem of the mechanistic interpretability or the SAE is we need to train one sparse autoencoder, and actually like a training one sparse autoencoder is cheap next to training like the whole like a cloud or ChatGPT model itself. The real cost is that it's a whole second pipeline. You run the full original model, right, on the huge amount of data to collect activations to train the SAE, and you store all of that. Then you train a separate autoencoder for each layer and each place you want to look. And in cloud ChatGPT or like any big models, we have a many and many layers, and there's countless of places you can like a probe to like a train an SAE. And the dictionaries here or like a storage here have to be huge into millions to billions of features, and they grow much faster with the model size. So every time with the base model changes, you redo it, you retrain the SAE. On top of that, I think like a fully reverse engineering a large model, a large language model, it's just so impractical. It's not doable. So to confirm that, the researchers at Google DeepMind, they also argue that we should pivot to what they call pragmatic interpretability. They steer from like a mechanistic interpretability, trying to reverse engineer the whole model, to pragmatic interpretability, meaning they just try to solve the concrete safety problems instead of chasing a complete map of the model. And the second problem is deeper, and I think it's more serious, and it inspires the rest of the talk. We need to set up two things here. First, an explanation is plausible if it looks convincing to a person, and it is an explanation is faithful if it actually matches what the model did inside. But the scary part here is they can come apart. A method can give you a clean, convincing story that has nothing to do with the real model reasoning. So last year, researchers ran sparse autoencoders on a random untrained network, one that computes nothing meaningful, and still got nice, interpretable looking features out of the SAE. So it's kind of bizarre. It was a pretty shocking result to me last year. So I think that, and is a recent paper, it's called like a dead salmon problem in AI interpretability. They echo a famous neuroscience example. So a team put a dead salmon into the brain scanner, and they scan the activity. So the fish was very much dead. But ridiculously, the scanners were just picking up the noise and the analysis dressed up as a signal. And people call this a dead salmon problem. So I think the takeaway here is post-hoc tools like mechanistic interpretability or SAE can give you plausible without faithful. They can, or like sometimes they can be faithful, but they can give you like something plausible without faithful. We will dive into faithfulness later. Okay, so that's it for the interp or like a mechanistic interpretability. Maybe I go too fast. I will pause here for any questions if you have. I'm looking for some interaction.
Jan, we have some questions. Just a second.
Hello, can you hear me?
Yes.
Great. So one question I have is the SAE, if you're boosting the Golden Gate signal, are people going in and adjusting weights kind of manually to accentuate those neurons, or are they training on like Golden Gate?
I miss you for the last part. So are you asking for the steering of SAE? Do people choose how to steer manually, or we have another way to automatically steer them Golden Gate Bridge?
Yeah.
This is a holy grail question of SAEs because right now most methods they do that manually. It means people need to steer the model at the right strength, because if you oversteer it, the model just give you the gibberish. It just say Golden Gate Bridge, Golden Gate Bridge, Golden Gate Bridge. But if you understeer it, it doesn't give you like something meaningfully about Golden Gate Bridge. So you need to find a sweet spot. So it's actually what most people are doing here right now. For the automatic steering, to my knowledge, they're just like one or two papers, but they are pretty premature. And how to steer is a huge question for the SAE. Does that answer your question?
Yes, thank you. And just one more question is if you see any difference between interpretability and explainability. Would love your take on that.
So you are asking the difference I see between interpretability versus explainability?
Yeah.
There's a huge and long debate about the two terms. But right now we are in the LLM era, so I kind of use them interchangeably and I don't see the huge difference between them. But back then, if we still working on like the old models, like image classification or like the more traditional models, there's clear difference between explainability and interpretability. I think we can get into this later because I think it takes a little bit more to explain it like thoroughly. Yeah.
Any other questions? Maybe, Jan, if I can just ask one question.
Sure.
I think you described rightly about the autoencoder structure, right?
Yep.
Can you also just like share some things with the students about how people are thinking move away from SAEs, like something like verbalizers, if you can? I'm not sure if you're covering that.
I missed the last part. Can you do it again?
Things like verbalizer, what people are doing now.
I see. So verbalizer. Actually, verbalizer is not specific for SAEs because you can put the verbalizer on any explanation methods. But my quick answer for this is people are still pretty much trying to decode the activation of the model into the natural language explanation. But I think it has the faithfulness problem because they are still training the model, the verbalizer, to reconstruct the activation instead of asking the model to faithfully show the reasoning, So, but I think one caveat here is if the explanation you have is faithful, so the verbalizer will be faithful. But if the explanation is just like activation, it's still a black box, and there's pretty much like uncertainty and a pretty much unfaithfulness going down there, and I think it's just harder. So the quick take is you can do verbalizer, but uh, I think like doing it on a interpretable by design model will give you the huge advantage than just like doing it on the activation of the model.
Perfect. And I think that is what we are going to discuss next. So, great. I think we can continue.
Okay, so sounds great. So now let's get into the next part of interpretability, and this one I'm advocating for it. So maybe I'm a little bit biased. So please pardon me in advance. So okay, now let's get to the by design interpretability. So if post-hoc explanations can be unfaithful, here's a question I want to ask. Can we just build a model that is interpretable by design? There's no second model to explain the first, and the concepts live inside the model itself natively. We don't need the concept discovery. We just like paint the model with the concepts. We can train the model with the concepts being specified beforehand. Can we do that? So here's I put like two approaches side by side, the post-hoc and the by design interp. So you can see the real advantage here of by design interpretability. We don't need the second model. And the faithfulness, when the post-hoc or SAEs, they're still facing the faithfulness crisis. The by design model, you always have the faithful explanations. And for steering empirically, we are showing that we can control hundreds of thousands of concepts. While if you just use SAEs or like a post-hoc methods, I believe you can just not just I believe, it's in the literature, it's showing that you can control several to just a dozens of concepts. And the cost here, I don't think like there's huge advantage of interpretable by design here. But the cost is in the post-hoc, we pay the cost after training because we build the model and we explain it. But by design, we pay during training. It means like we put like an interpretability into the training process. I will get into details later. But this is the difference between like a post-hoc interpretability and by design interpretability. Okay, so by design interpretability, let's take an example. This is stealing HB from Guy Labs, where I'm working at. This is the first interpretable by design language model at this scale. It's like a 8 billion parameters network. And here's the whole idea in one picture. So we have a prompt as the older candidate and the younger candidate applied. The better higher is. So the prompt goes in on the left, in the middle. Every prediction or every model output has to pass through a layer of human understandable concepts. And we have 100,000 of them. For this prompt, the concepts like job suitability and hiring context lies up. And the answer on the right here is a better hire. The answer here is the younger candidate. And the answer is computed straight from whichever concepts are active. You can just read which concepts activated and understand why the model chose what it chose. The explanation is not a separate analysis as we are doing with like a post methods. It's a real computation of the model. So I'm showing this the same way as the SAE slide on purpose. So
Yeah.
you can.
Okay, Dr. Nguyen, quick question, if you could back up one second. So in this prompt, the older candidate and the younger candidate, and it looks at human understandable concepts like job suitability and hiring context. What about older and younger in terms of potential ageism within the model?
This is a
I
great
know
question,
this is
but
an
I think you are going ahead of time. We will get into that concept later.
Okay, fair enough.
It just next few slides. Okay. So where will we? Okay, so I'm showing this the same way as the SE slide on purpose, so you can compare. So the difference is that the bottleneck isn't added on afterward. It's a part of the forward pass for our hiring question. The hiring question we had before. So hidden state from the backbone gets projected onto the name concepts, like job suitability is activating, hiring concepts is activating, the finance it doesn't, and sports it doesn't. Each parts, few of them light up here, and the answer is computed exactly from those concepts. So the explanation is just like you read out from whatever the computation giving you. Okay, so I think we go back to your question about the age. Actually, when we pass the same question, there's another concept lighting up is the age bias. We give the interpretable by design model a prompt, and actually it's at risk of the bias completion or like a bias answer, right? So the hiring question that mentioned the older and younger candidate, and it say that the young candidate. So we look at the what concepts are activating, and they are pretty suitable, the job suitability, the hiring context. But one of them, like a highly activating, is an age bias concept, and it lights up strongly, and you can see it directly here. And I think we can somehow conclude that the model is a little bit biased here. Okay, so here's the highlight. We take that age bias concepts and we suppress it at the inference time, and we rerun. The concept drops, I think, the activation from 0.83 down to near zero here. So completion changes to something about matching experience to the role, and this is important part. We never touch the ways like the fine-tuning paradigm. It's a closed loop steering. We diagnose a concept, we steer it directly, and there's no retraining or no fine-tuning. So if you compare that to like a fine-tuning, which will edit the weights globally and can quietly hurt other capabilities. So I want to stop a little bit for the question you raised before. Does it answer the question? I'm showing like actually the model is activating like some age bias when it say, hey, young candidate should be higher.
Good question.
Yes, it does. Thank you. And I guess just one more follow-up question to make sure I'm understanding. This steering, is that done through prompt and context engineering, or is that fine-tuning?
Great question. So as I show here, we train the model with many predefined concepts, and the age bias concept has been into the model even before training. We just train the model to be fluent for the next good prediction, but we specify at this neuron, this must be the age bias. So when we are seeing that the age bias is activating, what we did is we just go to that neuron, we turn it off, and the model will give you a totally, a completely different answer. So there's no prompting here, there's no fine-tuning here. We just know what concepts in the model is causing the bias, and we just go there, we turn it off, and that's it. Does that answer the question?
I think there are some confusions.
You know, so if you're not fine-tuning it, then how are you changing the model's behavior?
Oh, so we have the network here, and we predefine the concept. For example, we predefine the age bias there, and we train the model. We actually train the model from scratch for the next word prediction. And in the next word prediction training, the model learn to put the age bias context into the age bias concept. So the concepts are actually learned during training of the model. So it's different from fine tuning. In the fine tuning, you just have a pre-trained model and you do some fine tuning on it. But here we just have a pre-training.
I think we are good. Yeah, thank you. Are there any other questions?
If you have just just give me the follow-up questions. I think if I don't give you a satisfying answer, just follow up and we have a deeper conversation.
I think there are a few questions.
Okay.
Okay. Sorry. So you said that age bias is trained into the model. Are you going to talk about how that's done? Because that still seems mysterious.
I see. I think I skip that part in here, but I will try to explain it without showing the real technical report. We have a huge technical report for it. So in the training of the model, we just have the initial the randomly initialized model, and we specify that, for example, the neuron 0 inside the model must be the age concept, right? But must be the age bias concept. And when we train the model, we pass the data for the age bias concept, and we supervise that kind of neuron to be activating for that kind of data point. And for other data points, it should be not activating. So the concepts here are supervised during training of our model. We have another loss. I think I missed that. I said that it's learned during the next token prediction training, but actually we have another loss term. It's like a concept loss, where we try to supervise the concepts being learned inside the models.
Okay, the supervision part, I think, clears it up for me. But thank you.
All right, thank you.
I'm wondering, like, when you're creating like the conceptual, are you like manually defining all the different things to do, or assist with that, because it feels like if you're trying to like create a listed concept, explode really quickly.
Sorry, I think it was on and off. Chira, could you space it for me?
Sorry, I was wondering, like, when you are creating the list of concepts for the model to learn about, like, are you just manually defining each one, because it seems like that could get like really long really quickly?
I'm trying to understand the question. Can you do it again?
Yeah, sorry.
Speak. Concepts come from.
Yeah, like when you're creating the list of concepts, like, are you manually coming up with that, or are you using like another model to guide that? Because it seems like manually selecting like each concept could get really long.
I see. This is a super good question. So in the data annotation, we actually train our own concept annotation model, and we train it ourselves, and we then pass the training data like a normal training data, just text, and we pass to like the concept annotation models, and it gives us a list of predefined concepts. I think in total we have more than 100,000 concepts, and we do some filter out. So we went down to 33,000 concepts manually, not manually, like automatically annotated. And there are like more concepts we discover later. So everything add up to like more than 100,000 concepts. So yeah, we have our own like a concept annotation model for this kind of annotating.
Thanks.
Yes, and if you're interested in how we did that, we released a blog post, and it has everything. We released a technical report, and it has all the details about how we train the concept annotation model, if you're interested. Thanks. Great question. Okay, so I think Yeah, I should finish this part because I'm in the middle. Okay, so we were at the steering. We just go to the age bias concept. We turn it off, and the model is good. It has an answer. The one whose experience matches the role requirements should be hired. Okay, so now I think this is a fair question. So if you force the model to be interpretable, do you sacrifice its performance, like coding or math? So here's our empirical evidence. H dot is a model. Up is a benchmark on the math and coding etc. And the right is more training compute, more data on the log scale. So steering is a purple dot here. It sits at the far left because it uses the least compute of any model here. And look at great length. It beats like a comparable size models like a Llama 2 and DeepSeek 7B. And it stays in the same neighborhood as a model that uses 2 to 16 times more compute or data. So interpretable, you can see here, they are much more expensive to train, but we are in the like a same neighborhood. So interpretable by design model with the least data and the least computation still perform pretty competitively with other models. And here is a more interesting result, and it's actually a pretty surprising for us as well, because we found the interpretability does not get worse as the model gets bigger. Because in AIs, I think people always have an argument that the more you scale, the bigger the model, the more black box it is. But in our case, when we try to get the model interpretable by design, the interpretability just get better. And there's a reference here if you're interested in the metric here, or like how is it better, how much is it? And the concepts became more independent and more meaningful in the larger models. So the model gets easier to understand, it gets more capable. So we scale from 800 million parameters to 8 billion parameters, and we see this like keep increasing. So it's a super interesting result for us. So imagine if you scale it to like a ChatGPT or like a cloud size, and you get like a very capable model, and the model can still give you like a faithful explanation. So it should be great, right? Okay, so let me state the big picture here, because this is the conclusion for this part, interpretable by design. We usually treat interpretable as a cost we pay against capability. We tested whether that cost grows as the models get bigger, and it does not. It does not. The real change is where the interpretable enters. So in this model, in the standard recipe, when you train a normal model, right, you just train it with to maximize the performance, and then you go back, you use the post-hoc tools to discover the things, or like to try to explain the model very locally. And it doesn't, often it doesn't guarantee the faithful explanation. So we flip that entirely. We flip that paradigm entirely. We ask what conditions make an explanation faithful in the first place, and we build those conditions into the data training and the data curation, the model architecture, the objective, and the losses. And because the same concept variables drive both explanation and the control, so you can take an output, you see the concepts behind it, edit the one you care about without training. So in short, if interpretability can be specified, can be trained, and scale like any other capability, then the opacity of today's most capable models can be solved. Okay, so that's it for the part 3, interpretable by design. Before we look ahead into the future of AI interpretability and my text, if you still have any questions about this, I will give some time on it.
Yeah. So now that you've gone through the concepts, or the interpretability and its concepts. Can you apply that back to your example with ibuprofen? How would we catch that that's a bad answer?
Great question. I haven't thought about it. Let me look at it and see if we can have an answer. Okay. So I think in this scenario, we would expect to have a concept of reassuring or like overconfidence, or like I think something less cautious. But I'm not entirely confident about that because it totally depends on like the data annotation. If the data annotation can capture that kind of thing, that I think it will. We can like detect the model wrong answer or like any like model hallucinations.
Any other questions?
Oh, thanks for the answer. Thanks for the question. Thanks.
I think we'll continue, Chair.
Okay. So we finished 3 parts, and we go to the future of AI interpretability. Okay. So okay. So we said we need faithful explanations of how an AI reasons. And we just show that you can actually have them without giving up the performance, even at scale. So the question for the future is just how far can we push it? Let me give you like 2 directions or my takes. So direction 1, the first idea is to build or to put the interpretability design all the way into training. With the steering model from GuideLabs, we did not just add a concept layer at the end. We carry the faithfulness and interpretability constraints through the entire pipeline, from data annotation to pre-training, then through mid-training and all the way to post-training. And that is the point. When the constraints hold at every stage, you do not have to wonder whether the explanation is reliable or not. Whatever the explanation says, you can trust it. And the future direction is to push this further. For example, if you train the model to the RLHF or DPO, so we should put the interpretability or like faithfulness constraints into the reward objectives or like agent training, or like put into like the proactive agent pipeline right now. And another direction is automated interpretability. So I think it's somehow related to the question about the verbalizer Chirag asked before. So right now, a human reads these explanations, but I think it's so impossible because there's so many to read by hand. The information is too dense. I think like I get headache sometimes just like looking at the model thinking and to try to justify the model answer. So we can let an AI read them instead. I give an example here in the loop. So a model makes a decision and its concept light up. An AI model, like you can use ChatGPT, Cloud, or like a your model itself, this model itself, reads those concepts, spot a problem here. For example, the bias concept on our hiring question, steer it down and fix it. So humans is not in the loop. So I think that's something people call self-recursive AI. I mean, like it has so many variants, but here I just like try to initiate a instance with interpretability. And pretty much I believe in the self-recursion via like interpretability. And the same idea here can also help people. When the computation is too dense for a person to read, and an AI can digest it and hand you a short and faithful model reasoning insights. And actually in GuideLabs, we are building this kind of idea. So my design is very important here because the AI is reading concepts the model already exposed. So the reading is reading something faithful, and you can choose the verbalizer as well, and you can put some constraints to verbalizer to make it even like a faithful and make it useful for the downstream task. Okay. So here come to the last slide of my talk. Let me bring everything together with a quick recap. In part one, we learned about AI interpretability. In part two, mechanistic methods like SPA autoencoder or SAE open up the whole model. But we saw that post-hoc explanations can look plausible without being faithful. And the part three, by design, brings the faithfulness in. So the explanation is a computation itself, and it scales all the way from 100 million parameters to 8 million parameters of LLMs. So the shift is going from explaining an AI after the fact to designing one that can understand from the start, from the beginning. So that's the whole talk. You may ask where you can actually try the interpretable by design LLM. We built the steering. So we open source everything for the model on GitHub with the link here. And this is my website for more information, or like if you have any follow-up question, inquiries, please take it away. And now I'm happy to take your questions. Thank you very much for listening.
Thanks, Jen. Let's see if there are any other questions.
Regarding turning off neurons or adjusting weights, if there's a concept like gender bias, is it coming from like a class imbalance where there are too many examples of, let's say, like men playing sports or whatever, some gender bias towards men or women? Is that coming from too many examples of one or the other, like a class imbalance, or is it coming from training data that says, no, like, men are better at this thing, women are better at this thing?
Excellent question. So I would say it's coming from the data, because the main training objective is still next token prediction. And actually the model is just saying whatever it see in the training data, and when the data is imbalanced, so the model just spit it out. But the good thing here is we can actually see that the model is being biased by looking at the bias, for example, gender bias, highly activated, and we can see it and control it without, go back and fine tune it, like add more data for like a man or women, and fine tune it without, knowing the whole culpability can be correct or not.
Thanks.
Any other questions? Anyone? People on Zoom? Okay. I think this was great, Jiang. Thank you for taking the time. Jiang is in California, so he's doing this at 6 a.m. in the morning. So let's thank him again for doing this.
Thank you very much for having me. I really appreciate it, and I appreciate all the questions, all the great questions you guys raised here. And any follow-up question, or you wanna talk about interpretability, about San Francisco, about the job, the research, just follow up on the email the website.
Please share the slides, Jiang, whenever you can. I'll share the slides with everyone, and then I'll share your email ID as well if anyone is interested in any internship or jobs. Great. Thanks again.
Thank you.
Yeah, I'll be in touch.
Thank you.
Bye.